Welcome to topic 8.3, electric fields, daily video number 1. In this video, we'll define electric fields and predict the results of charge interactions. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Before we go diving into solving a bunch of problems, let's review a fun little concept like gravity, in particular gravitational fields. So you have an Earth, pretty cool Earth, I drew that. That is going to bring this gravitational field that's all attracting towards it. We know that because if you drop an object, it falls down, so on and so forth. We know that when you get closer to the mass, it's going to have a stronger gravitational field. And as you move further away, it's going to get weaker. Other masses, so if you have a rock, once again, it's in the same direction as the gravitational field. Masses follow the direction of the gravitational field. Well, near the surface, one other thing, which is what you know when you're in the world around you, we have this equation, right, that says that gravitational field, or the acceleration due to gravity, is a constant. Why is it a constant? Because you're so close to that surface that doesn't matter how far you get away, you're not really changing all the electric field lines or gravitational field lines into being parallel. So if we send a little gazelle in here, for example, it'll just go leaping across, doing its normal thing, having a wonderful time here on Earth. Let's keep this idea in mind as we talk about electric fields. Oh my gosh, does that picture look familiar? I think it does. If this is a negatively charged sphere, it creates an electric field defined by the direction a positive charge would move. So if I have this negative charge that's there, sure enough, we know that negatives and positives are attracted. So I put a positive charge next to it, it's going to fall down towards the surface, just like would happen with gravity with masses. The closer you get to the charge, the stronger the field ends up getting. One thing to note, right, is that positive charges feel in the same direction, just like mass would do. However, negative charges go against the electric field. This would be like if we had negative mass. It doesn't exist, but if we did, it would go the opposite direction. That's what electrons do. They go against the electric field. We can actually see that in this equation. The electric field, the vector, is equal to the vector of the force over charge. Well, if these are vector quantities and there's no magnitude symbols, that means that if this Q is positive, then Fe and E are going to point the same way. Makes sense? But if Q is negative, that's going to flip the sign and make it so the force is in the opposite direction of the E field. Let's see this in a little example. We have an electric field traveling down. I take a positive charge, and if I send it through, which way is it going to go? Yep, it's going to go down. It's going to follow that kind of parabolic trajectory. On the flip side, if I put a negative in there and send it in, it's going to go up. So sure enough, if these have the exact same mass, we weren't doing an electron and a proton here. If we had the exact same mass, we'd expect that one would curve up, one would curve down, one with the electric field and one against the electric field. So that's a difference that we have when we talk about electric fields versus gravitational fields, that we can have different charges interacting with that electric field. One other thing to kind of note is gravity and charge, or electrostatic force, I should say, are monopole sources. You'll learn in future units, in particular unit 12, about magnetism, and those are dipoles. But magnets are the only dipole sources, and then monopoles means that there's only one thing. They can only have electric fields going into it or electric fields going out of that system, as we see modeled here. We also have this idea of a test charge in physics. What is a test charge? Just like we thought about if we drop a mass here on Earth, it falls down. That's because that's what mass does. We define electric fields by the direction that a tiny little positive test charge would go. So that's how we determine the direction. And we determine the magnitude based on how strong the force is on it. So let's take a look. If I put this tiny little positive test charge there, it might feel an electric field that's attracted towards it there. And as I place it in a bunch of different places, all around and about, they're going to end up always being attracted, but get stronger or weaker based on where they are. So test charges are just something that we put into the space that doesn't modify the field at all. We're just kind of conceptually saying, what if I put something there? What would it feel and how strong would that electric field be at that location? That's what we're looking for. So with that in mind, we can combine this idea of Coulomb's law, where it's forces, with the electric field. And if we put these two equations together, we get something that looks like this. A key note, this equation is not on your AP equation sheet because it is only applicable for point charges or objects with spherical geometry. So it's a great, I don't want to call it a shortcut, but it's an equation that if you're dealing with a point charge and trying to find the electric field outside, you can just combine these two equations together and everything works out great. But you have to remember, this is only for point charges or spherical geometry. So let's practice a couple little problems here to make sure we know how this is going to work. Let's compare a helium and a calcium nucleus. Just as a quick note, don't worry about the periodic table in terms of knowing charges or masses of things. We're going to give that information to you in the problem. This is really just more for context. Because why not talk about real things? So for helium, it travels to the left, experiences a force which we're going to call force Fe. Calcium nucleus that has 10 times more charge moves through the same field twice as fast to the right. So this one is going left, and that was end up going right. Experience a magnitude of FCA being the force on calcium. So what's the ratio of the magnitudes of the force? Give this one a ponder. And let's give this thing the answer. The answer, sure enough, is A, 1/10. How do we know that? Well, not 1/10, but 1/10. If we look at our electric field equation and we manipulate to solve for F, we're going to see that F of the helium, force of helium, is going to be EQ. The force on calcium is going to be 10, E times 10Q, because it's 10 times the amount of charge. You might say, well, what about which way it was traveling? That's not going to affect the force. Also, if you mention like, what about it going faster? That also doesn't affect the force. The only thing that affects the force is just the E field, which was the same, and the magnitude of the charge. And since calcium was 10 times greater, it's going to have 10 times more force. Let's give one more a try. Let's say we have a charged sphere, has its electric field at point P, and I move point P to be 3 times as far away, and we double, I believe that's what it says there. Yep, there it is. Double the charge of the sphere to be have twice as much charge. I want to know what the new electric field is going to be at some point way out yonder. So give this a ponder. If you want to pause, you can. But the answer would be 2/9. Why is it 2/9? Let's break this thing down. We're going to jump to that equation that we derived before, where we combine the Coulomb's law with that definition for electric field. We put these two things together, we get this equation. We're going to do this thing called the ones method to help us out with our proportional reasoning. What's the ones method? The ones method is when you turn everything into ones. Sure enough, 1 times 1 over 1 squared is just going to be 1. That was the initial case. But now let's look at what the new case is going to be. The new case was twice the charge and 3 times the radius. Well, that means my new result is going to be 2/9 of what it was initially. Because if my initial case is 1 and my new answer is 2/9, that is by definition 2/9 of 1. So that's where it ends up being 2/9 of E0. Excellent. So what should we take away from this first video? Main thing we should take away is that electric fields defined by the direction of positive charge will move. Just by definition, we pick that by convention. The other thing is that the electric field can be determined on E equals Fe over Q. In topic 8.4, you're going to learn more about how we use this for charge distributions. And then this last one is that for point charge and spherical geometry, we can learn this last equation that was the combination of both Coulomb's law and the definition of that electric field that we had up above to result in this new case. Thank you so much, and I look forward to seeing you in future videos.